allow me to welcome allow me to welcome Dr. Kanishka Tyagi to come to our seminar to give us a presentation about machine learning algorithms in autonomous driving. And Dr. Kanishka Tyagi received his bachelor degree in 2008 India, and he received his master and PhD degree from at the University of Texas at Arlington in 2012 and 2017, respectively. So currently, Dr. Tyagi works as a lead machine learning autonomous driving scientist at Aptiv Corporation at California. And before that, he worked at Siemens Research and interned in machine learning groups at the MathWorks and at Google Research. And Dr. Tyagi actually had a lot of publications and won a lot of awards. Especially, he has published over 25 papers and filed 15 U.S. patents and trade secrets. That was highly impressive, Dr. Tyagi. And we really would like to thank you for giving us this talk. And please feel free to take it away.
Thanks, Dr. Kelly. I think as she said, my name is Kanishka. And I'll be talking a little bit overview and a slight amount of details into the world of autonomous driving. I think it's pretty hot, and it's a lot of job opportunities. There are a lot of open research problems. I'll be going through them during the talk, and feel free to stop me somewhere if you have any questions. And I mean, I can take general questions and all for sure.
Thank you very much.
Just to make it sound catchy, I gotta write this secret sauce to train machine learning. But there are a couple of, I think designing, I can see designing networks or training the neural network is more of an art than science to me. So yeah, there are a couple of tricks and hacks. So all right, so let's see how this works. Okay, so a little bit about me. I mean, I've already been introduced and all. So
would you like to? Sorry to interrupt. Would you like to put in the presentation mode?
Oh, it's not? Oh,
no, not yet. We're still looking at the.
Oh.
Yep, probably it's the monitor setting.
Yeah, it is a monitor setting. I think I know how to fix it. The primary monitor. Okay, there you go. Let's see now.
Yes,
how about now?
We can see that right now. Okay, perfect.
Okay, perfect. Okay, so I mean, I work primarily with all sorts of radar applications. Moving objects are kind of normal for a radar, but I work primarily on stationary objects, which is still an open problem to solve. Just by using radar, you can kind of detect things like 200 meters in front of you, and those kind of algorithms. So yeah, most of my time is spent in coding and then writing sort of hardware applications for machine learning. So my main work is into actually embedded machine learning stuff. So that's about me. Let's see. Okay, I got to put this because of my company large. So sorry about this slide. Yeah, everything has been taken from Google Research, and then all that information is in the public domain. Yeah. Okay, so let's see the talk now. So I'll start with a brief introduction to the problem that we have in autonomous driving, the sensor stack and the hardware stack, most of the common sensors that we use, and then give a little overview of how do we use machine learning in the autonomous driving case, and then get into more details of it. And then if time permits, I'll go through one case study where there is a typical problem of understanding a typical scene in, let's say, a highway scenario or an urban scenario, and then we'll go from there. Okay, so let's see the introduction. So just to motivate the problem, why do we need this whole thing? Why there is so much of interest in this? Well, most of the time, it's a bunch of things actually, but humans are terrible drivers. That's bottom line. We're terrible in this. So that's one thing. So roads will get safer if humans don't drive. It's very counterintuitive actually. We believe we are good in driving, but actually we are bad if you see the statistics. The number of accidents that happens, majority of the time, it's the human element that kind of gone wrong. And then it reduced traffic congestion for sure because it's more optimized for a computer is able to do it. And then you have definitely the whole parking lots that can be used for other things. But the last one is the one which is very interesting, which is very that's where the investors kind of get interested. It's a new business model where it's almost like, think of it like Netflix. or any of these streaming service, you're gonna be subscribing to the car rather than buying the car. So in corporate, we say we are probably the last generation which is going to be buying a car. The next generation to us is like the Uber and Lyft people, and then after that, it's going to be just subscription. So you subscribe, so you ask for a car, the car come by itself. You go wherever you want to, like the destination, and then you just drop the car there. So there is no concept of owning the car. So that's a new business model that people are interested in. And actually, Volvo actually works on this right now in a very initial form, where the nearby dealer actually drops the car to you on a monthly subscription. So that's there. So what are the typical tasks do we have for driving? The first is the lateral control for a driver. You know, you got to do some lane changing, you got to steer left and right. And then there is a longitudinal control, which, you know, in front of you, like you got to brake, you got to accelerate, or you get into a cruise control mode. And then you have some kind of objects and some kind of event that happens in front of you. And then you have to have an appropriate response for that. So it can be a stationary object in front of you. Let's say, you know, those tires that are there, the open tires, and then sometimes there are some objects, some dead animals are there on the road. I mean, you see all sorts of things on the road. And then there are some near moving objects, for example, pedestrians. If you're driving in near a park or, you know, near a shopping mall, you got a lot of slow moving objects. And then of course you have to plan it. For example, when you're overtaking a truck, let's say, that's a very good example. You really have to plan your speed, but at the same time you also have to be safely sort of go in front of him. You don't want to drive just next to him or next to the truck. So this is where we are right now in terms of the level of automation. I'll just quickly go through this one. Right now we are level 4. Level 0 is what we are right now when we do not have any autonomous driving. Level 1 is the basic, you know, the cruise control, the lane assistance and everything that is already there in the cars. Level 2 is what GM Super Cruise is, which is you literally can actually drive the car as long as it's within the lane. It can do that, and it can accelerate, deaccelerate. It can do that. Level 3 is it's coming in Audi A8 now, where it can actually detect the object in front of you and can have a response by itself. So that's the picture kind of makes it more easy. I mean, the guy's kind of relaxed there. You can see on level 3, but level 4 he's kind of completely mind off. I think that's where the challenges are. So it's think of it almost like this: getting a machine learning model to 95-96% is relatively easy, and then getting that 0.5%, and voila, you publish a paper in there on an ImageNet and all. So yeah, getting that last thing is the one. The corner cases is the challenge. So level 4 is where most of the corner cases are seen, and of course level 5. So for example, one of the corner cases in the event of a fastly coming object in front of you, what should be your response? Should you sort of steer away, or should you just sort of reverse back, or what you should be doing? Or if like if you're going on a highway or on an urban environment and you see an old lady crossing and a small baby crossing, and you know you're going to hit one of them, what you're going to do? Now these are like ethical.
Sorry to interrupt you, Dr. Tyagi. I think we have a question from the audience.
Oh, yes, please. Do I see the question somewhere, or is it?
No, he hasn't.
No, I just raised my hand.
Oh, I see.
No, just very curious where Tesla fits in any of the Tesla cars.
Well, if you listen to Elon Musk, they're on level 5, but on Planet Reality, they are on almost level 4 and level 3.
Okay.
They're somewhere. Great. So there is one more level in between, which is like 3+, and you go 3.2, 3.5. But they are somewhere in there. But while you're talking about Tesla, I mean, every OEM has a different concept of sort of visualizing or sort of getting into the autonomous driving. Though Tesla is focusing completely on camera. They want to solve the entire problem with the camera. So they get into trouble of, let's say, snow, rain, and night conditions. I mean, camera is kind of hard. It doesn't mean that it cannot drive. Yes, it can drive, but is it safe? Is it something that can take the corner cases? Anybody's guess. that's where the radar kind of helps it out. So other OEMs, most of the traditional OEMs, like BMWs, Audis, and other OEMs, and I don't want to name more, but most of the OEMs, they want to take the more traditional approach. I call it a Detroit culture versus a Silicon Valley culture. Tesla is more on that, just go fast, it's fine. One or few accidents is fine. But like one accident causes a lot of problems in terms of investments and everything. So our company, or most of the traditional way is of one way of doing it is like you take all the sensors together and then take the best out of each sensor. Radar is very good for nighttime, driving, fog, rain. There is no problem. Camera is really good for other conditions. And then again, LiDAR, so that's there. So yeah, and then level 5, no, we are not there anymore. I mean, that's going to take a while, actually, irrespective of what, somebody tweets. That it's going to be there now. It's going to take a while. There are a lot of corner cases, and even anybody working in it internally, like technical, knows it. Like it's going to take time. So that's there. All right. So so this is just one example of objects in front of you. I mean, you see all sorts of things in front of you, and sometimes you gotta have the appropriate response, and sometimes you have to stay away. For example, in the rightmost, the bottom right picture. You see, you have to sort of detect it, segment it, and then sort of understand what's going on, what's the limits and everything. So yeah, these are the things that mostly happens on the road in there. Now let's get to the sensor and the hardware stack. So this is just a brief summary of major sensors that we actually use onto the car. And then as one of the questions was there, we just try to come together with something that is useful from each of the sensors. So I'm just showing it here that which sensor is good and what. And then one takeaway from this slide is like sensor fusion becomes very critical. Or the other problem is called conflict management. A bunch of papers are written on that, but that's one critical area where there's a lot of research going on. So these are just for the sensors, and then we also have other sensors onto the car, which kind of helps us, like GPS, IMUs. I think that will be coming on the next slide. Yeah. So yeah, the GPS and all, it kind of helps us in it's mostly for the mapping, so that it's mostly also for the planning that we are doing to go from point A to point B, and then what's the shortest, what's the fastest, fuel efficient, and all those things. Because remember, ultimately we want to plan the entire system completely autonomous, and human intervention is bare minimum and close to zero. So that's there. And then of course you have the wheel odometer, which kind of tracks the velocity of the vehicle that is there, and then the overall orientation. These things, if I go a little bit more into detail, these things kind of helps in working the entire system, all the sensors that are there, which I'll be showing in the next slide, working in synchronous, because every sensor has a timestamp, and it's really sort of tricky to make that timestamp for all the sensors to work in all together. That's a very tricky work when it comes into play. So I'm just showing a very typical sensor setup that is in a car. By no means it's exhaustive. There are a bunch of other sensors also. And you have the front-looking radars, which are really far-range radars. I'm talking 200 to 250 meters in detections. You have the side-looking radars, which I'm talking 80 meters, close to 80 to 100 meters, mostly. And every radar and every sensor has a specific purpose. I mean, that just sort of justifies the location there. And then you have different cameras for different sort of situations. And then the LiDAR on the top. Again, Tesla or any other company, I don't want to point to one company, but it's like, some companies, they don't want the LiDARs on top, and it kind of makes sense. I'm one of a very famous OEM, like luxury OEMs. Imagine a Ferrari having a LiDAR on top. I mean, it's hard to sell it. So it's a lot of those marketing things also that comes in. I mean, people buy these cars just for the looks and everything. You don't want like a police siren on top, like a LiDAR running around. So LiDAR has its own issues, but LiDAR makes the problem really easy actually for us, because it creates a 3D point cloud compared to a radar. And then you have the IMU, which is just to sort of locate the car in the world coordinate systems. So in the next slide,
Sorry to interrupt. I think we have a question from Stefan.
yes, please.
Oh yeah, sorry, I didn't know if we were interrupting or not. I'm
No,
sorry,
it's
but
fine. It's fine.
so when if you can clarify very generally, when you say radar, so I've taken like a radar class, but the radar I learned about is like giant, like it's for airplanes and it like spins around.
The SAR radars.
Well, we also learned about synthetic aperture radar, but we also learned about like ground-based radar and stuff like that. So, what is this radar? Like what's like?
Okay. Yeah. This is
clarification.
Oh yeah. This is an FMCW 77 megahertz MIMO radars.
Okay.
These are very specific to autonomous drivings.
Oh, okay. So there's like a general kind of like type of radar you can use for autonomous driving.
Oh yeah.
Okay.
You have to. So I mean, there are a lot of companies, not just Aptiv. Like we have our own radars. We manufacture our own radars, but there is also from Bosch. There is also from Continental. There are a bunch of companies that are doing this.
Okay.
Arbe is another one that's pretty cool.
Okay.
But yeah, this is a very specific, tailor-made radar for autonomous driving.
Cool. Thank you.
Okay. Any other questions? Okay. So yeah, this is another general setup that we have right now. If you go to Vegas, you order a lift. There's a good chance it's an Aptiv car kind of comes in, and in a white. I think it's a white BMW, I guess. So yeah, we have these long range. So the thing I was mentioning before, we have these long range lidars. We have these side looking radars. We call them SRRs and ESRs. And then you have this whole computer, and that's, in terms of research, that's combining all the information from all these sensors and then bringing it all together into one. That's a very sort of a critical area of research, and I see a lot of papers on that also sometimes. I mean, in the recent conferences on the transportations. But that's a very good area. I would highly encourage. Combining all the sensor fusion is a very, very good area, I think, to work on. Okay, so let's see what kind of hard. Yeah.
Oh, probably. I'm sorry to interrupt, but probably you're gonna talk about this later. I'm just curious about the computer on the car. Is it really power constrained, or do we really want to minimize its power and size? Because I think I see a lot of.
That's a good question.
I think a lot of papers are discussing that this computer on the car is power limited, and we want to make it smaller and smaller. I'm just curious, is that a real need?
That is, yes. So that's a need. I'll give you just one example that might help. A major OEM had a problem when we increased the sensor cost by 5 cents because they're selling in millions. So that's how much the margin is. I mean, in cents. So if somebody's fighting over cents, it's hard to convince them that how about you put a GPU on your car? No, it's super hard. And that's where actually I'm jumping ahead actually, but that's where the idea of actually training smaller networks, smaller neural networks actually comes in handy for us. And surprisingly, that was my PhD topic, to sort of design smaller neural networks. So that's where it actually comes handy. But yeah, you cannot put a big fancy computer into the car. I mean, again, car aesthetics, everything plays a role on this because they have to market it ultimately it's a consumer product. So, it has its own constraints there. So yeah.
Okay, good to know. Thanks.
Yeah. So yeah, like I said, so what kind of hardware do we have? Well, we have hardware at different stages what we are doing. So the first one, mostly the workflow goes that you work it on your local laptops that you have. You have a proof of concept that you want to have. And then it goes, and that's what I'm calling as the offline hardware. Mostly it's a laptop, and then it goes on to some high-end workstation. You use Lambda machines, mostly that they're the most common things. Which have 4 or 5 GPUs in there. And the idea there is that can you actually train, and I'm talking very specific to training a machine learning or deep learning model here. So let's say you run it on your laptop with a GPU, so it runs in there. Then you go onto a little fancy workstation. and their workstation has at least more than one GPU. So now you're doing a distributed ML training. So you know, okay, it's going to run on multiple GPUs. There are packages for that, like Horrorwood is one that is often used. I find it personally very easy to use it. It's kind of straightforward for distributed computing. And then you take it onto the cloud, where you have like 500 machines or 600, whatever, some machines and all. I mean, Amazon, Azure, whatever works. And so that's mostly the workflow. And most of your data that is there, it's all on the cloud. You do not put it on your local server. We are talking petabytes of data here. So loading the data by itself is an issue. So there is a whole set of you have small tiny data sets that you run on your own machine local. So I'll give you an example. Let's say you come up with an idea. You say, hey, probably this might be a good improvement into this. So what you do mostly is, and there are many ways to do it. So I'm just saying the one that mostly works for us in our company. You work on your laptop on that specific idea. Then you push it onto the high-end workstation where the main code base is, the main Git is. Make sure it gets merged into it and it runs on multiple GPUs, and then you push it onto the cloud. See if it runs. Get your trained weights and everything. Pull it back. See if it runs, and then you actually put it onto the hardware, onto the car, and actually drive the car and see if it actually works. So there is a whole loop in there, and I'll be showing that entire block diagram that I'm saying. So that's there. And then the last thing here is the synchronization hardware. As I said, timing is extremely critical in this whole thing because every sensor is working on a different time or a timestamp. So getting the timestamp correct is very, very tricky. Mostly GPS is actually used to provide a sort of a common clock. That is it. So everything works based on that. So whatever is the GPU GPS clock is the clock for the entire car that you have. Okay, so let's get into the machine learning and autonomous driving. How does it actually work?
I had a quick question before
yes,
you
please.
go on to the next section.
Yes, please.
You might touch upon this later, but for the technical details, like when you have all these sensors in the car, I know I'm familiar with they have like a CAN bus that synchronizes all the communication between these sensors. But I've heard that CAN is kind of outdated. Does it support like newer and newer technologies like the radar, which are high bandwidth? And can you also do like the precision like timing on the CAN, like using the CAN specification?
Yeah, that's a good question. CAN is outdated, yes, but at a given time, having all the sensors all together updated at the same time is kind of hard. So you end up working with CAN because everything else will for sure work with it. If you take a really advanced data acquisition system, most of the old sensors may not work with it. It's like, taking something that works, even though it's not outdated, it's a little bit outdated, but it kind of work. You kind of very sure that it's going to work with everything, even the advanced ones. Okay. Because that reminds me something. There is one more thing that actually happens in there, which is the throughput or the data coming in ingestion is another big challenge. There are ways to fix it. I mean, you do subsampling most of the time, and or you kind of slower the clock. There are some ways of doing it, but the whole timing of it is another talk by itself. Like, how do you do the timing correctly?
Oh, okay.
Yeah, but I can tell you like that most of our time is spent in that, in getting the timing correctly, getting the training model correctly, those kind of stuff. And then maintaining the database by itself is also an issue.
Okay. So, yeah. Interesting. Thank you so much.
Yeah, no problem. Talking about data, how do we actually store that? So majorly the problem is divided into two. One is the highway setting and the other is urban. Highway you might know by now. I mean, highway is pretty much solved because there are very few things on a highway that you need to worry about. I mean, and then urban setting is the one where most of the problem comes in. You have all sorts of turns in there. The number of lanes are, it's a little less, but the cars are pretty close, especially in California here. I mean, you go to Santa Monica or somewhere, in downtown Los Angeles. It's really, really like the lanes are small. Everybody's like, and as I said, people don't drive that nice. So, I mean, New York or LA or in all these major cities. And then the traffic volume is a little bit lower than the highway setting. But in a highway setting, the number of intersections are fewer, but the only problem that we face in highway setting is the objects that suddenly comes in the edge cases that are there. So I'll just give one example of a highway, just to prove you that highway setting is easy, but there are some tricks in there. This is a good example of it. Now consider this white car which is behind the truck. It's supposed to take a left turn, and it also had to sort of match the speed of the truck so that it doesn't collide with the truck. But at the same time, the car in the blue, which is on the one lane left of it, might also take a turn towards right side of it. So when the white car, which is maybe I can point it. Does my point? Can everybody see my pointer, or
Yes.
doesn't?
Yes.
Okay. So when the white car actually takes a left turn, it has to see two things at the same time. And I want to stress on the point at the same time, that whether the blue car is going to take a right turn, and it has to sort of speed up or speed slow based on the truck speed, because there is a chance that the truck also speeds up. So this is just, and I'm really going through it fast, but actually there's a whole details about it. And how do you actually do this, maintain the speed, change the lane on a highway setting, especially when there's a lot of crowd in there. So this comes under planning. Actually, how do you plan this? Okay. See. Yeah, this is a typical pipeline for any machine learning training that we have. You have the data lake, which is again in an online and offline mode. All your data is in there. That's connected to your cloud, where everything, whatever data you've collected goes into the cloud. You take in some data from the data lake temporarily for your training, for your proof of concept that you want to have, and then you do the labeling. The labeling is a time intensive and labor cost, which means a lot of money gets into it. So anybody coming up with algorithms for maybe semi-automatic labeling or anything like that is very valuable. So that's another area of research. I feel like, how do you label things, or how do you at least get some unsupervised learning part in a much better shape? Because having these labeled data, most of the time we work with the labeled data, which is pretty straightforward. But then in real life, it kind of gets tricky, especially the edge cases that are there. So yeah, people get every company has their own way of doing the labeling parts for there. And then you train it on the clusters, on the cloud. You save the best model that you have. And then you go through this data simulation. So before you actually drive the car for testing, you actually test it out in a simulated environment, more like a video game. You test it out there, and then you sort of fine-tune your model there. And then tune it, get the best model, do the simulation again, and then store the model. And then you finally deploy it. Deploy it onto the car, see how it actually reacts in a real environment where you have no control over the environment at all. And just drive it in there, come back, see what are the cases, and then the cycle repeats. So that's mostly, yeah.
Sorry, I was going to ask, sorry to interrupt. So for this data simulation, I think it's sort of critical to verify whether the model is working correctly or not. Is it?
Yes, that's correct. So
and
this
does
is
it rely on? Sorry, does it rely on the data we collected, or it works on its own?
So it is a completely independent identity that we want to have, and that's intentional because we want to simulate the real world environment there. So there is a separate team, which is, you can think of, it's almost like a video game there, where we are running it onto a simulated environment, and you want to actually test out things that it hasn't seen yet. So the basic idea of the machine learning part, where we say, hey, has it generalized well or not? That part is tested out into the simulation. And plus, it's easy to do. You don't have to really go out into the sun or something, drive the car. But then, just because you've touched that point, we face a lot of problem in the machine learning training because most of the time it ends up memorized rather than generalized part. And so regularization plays a big role into our training. We don't even realize it, but it's kind of sometimes overfits, or because if it hasn't seen yet something and it's yet able to do it, The other thing we do not know is the basic assumption of the network is the IID assumption. It's kind of hard because the identical and independent distributed assumption may not work in the real life environment that is there. So then how do you fix that part? So yeah, those are the corner cases that happens. So if the things that you're seeing is within the same distribution that you train the network, well, you're good, you're fine. But problem starts coming in when it's not there. So yeah. This is just a basic software architecture. I just put it into a block diagram way. The main part here to focus on is the environment perception. Majority of papers are written in that area, perception area, and it's a good area of research. But I would say system supervisor, which kind of takes care of all these parts and all, is also sort of worth looking into research. So yeah, I'll just quickly go through this. Machine learning doesn't work on one specific parts in there. So as for my own self, my daily job, I also have to look at different autonomous driving tasks and then come up with some kind of a strategy. Hey, maybe we can replace this whole system with a machine learning system. So it kind of works in sort of pockets way rather than there is a whole system. That's one school of thought. The other school of thought is, well, all you have to do is just think of a machine learning like a black box. Just throw in the data, have some labels, and let it figure it out. That's what we call end-to-end learning. Each of them have their own advantage and disadvantage, of course. It's kind of hard to isolate the problem when it goes wrong in an end-to-end. So you cannot really pinpoint, oh, where is it exactly going wrong? And but then again, it's most of your majority of your time actually goes in just training the network, and that's it. And you just keep feeding in more data, just keep training the network. That's it. The first one I personally feel is kind of more. It's more technical. It's more scientific. I feel the end to end is more of like a brute force way of doing things. In a block by block approach, the first one that I'm showing here, you kind of create a physical model of each of your system that you have. So you can really pinpoint where the problem is coming. And you can isolate that problem and then fix it and sort of put it back. So it's like a block by block approach that you take. And this paper is really good, actually. It's kind of showing this thing, the paper I'm referring here. Okay, so yeah, I'll touch on to the perception because I feel that's what majority of the people kind of like in the academics, I guess. So
sorry to interrupt. Yeah. So before you proceed, I'm just curious, is it popular right now that people will use one model for one task, or they tend to mix those tasks together into one giant model? Or maybe we call it multitask learning, multimodality learning.
Yeah, we mostly go with each model solving one task, and then there's sort of a supervisor which kind of combines it all together into one.
Okay.
Something like a HydraNet.
I see. I tend to have the feeling that a lot of people are starting to investigate the multitask and multimodality learning in autonomous driving, but I'm not sure whether this is a valid approach in reality.
I mean, it is definitely one of the approaches that people have taken, of course. But then there are other things in there. So this is the one I'm showing it here. It's kind of because you have many tasks to sort of do. Like you have to do the planning, the detections, the perceptions, the segmentations. So you have to do all of them. So it's really hard to put it all together in one. So the sort of the low-hanging fruit there, so to say, is that you just pick up one task, solve it once, pick up another one, and then somehow sort of merge it. There is something called, actually I work on it. It's called model inclusion networks, which is kind of fusing two neural nets, or let's say even if one of them is not a neural net, just fusing two models and then giving just one answer for that, or more than two models actually. So that's mostly what people tend to do.
Okay, cool. Thanks. That's very interesting to know.
Yeah, it is. Okay, so ML in perception. I mean, these are those four basic tasks that any sort of perception module will do. And each of them have their own problems in there. Just to say, again, this is a sort of very basic and all, and it can, and each of these problems get really complex. So, for example, classification. Classification of moving objects is fairly easy, but classifying stationary objects at a far distance, it's kind of tricky to do. Just imagine a situation: you have an object, or let's say you have an ambulance right next to, onto the, if you're driving, you're like on the right hand side of the lane, and it's a stationary. Detecting it at 200 meters with a camera is impossible to do, because it's like a point object there. But then doing it with any other sensor, let's say a radar, is also really tricky to do, because most of the time when you're driving the car, the ambulance is metal. It's standing next to a guardrail, which is also a metal. So when the signal that comes back is kind of fused signal. So one area of research is how do you sort of differentiate those two, the vehicle from the guardrail, and then sort of detect, because radar is able to see it, but it's not able to figure out whether it's an object really, or is it just a guardrail that's there. So that's an area of research. Okay. Again, that's just a software architecture. I'll skip this slide just to make it faster. Okay, these are just a few of the tasks that we have in perception. I'm talking more from every sensor, most of the three common sensors: the camera, the lidars, and the radars. The radars do a lot of tracking, a lot of detections. I'm not showing detections here, but actually radar does do a lot of detections, and again, it's an area of research. Most of the papers that at least that I've read on radar, they are able to detect things, but it's at a very, very small ranges. So if you detect something at, let's say, 60 meters, and you're driving a car, probably it's too late. You might crash by that time. So you got to detect as far as possible. That's there. So yeah, any questions so far? No. Okay. So yeah, let me get into just briefly into the models that we actually use in training these systems. And like Kelly asked before, we try to make the models as small as possible when it comes to deploying it onto the car. And when you're training it depends on the tasks. So here what I'm showing is more of the how do you design these smaller models that you want to put it onto the car. Because again, smaller models means the battery is going to be sort of used comparatively less, and then the processing will be, processing will be fine, but then the latency, the bandwidth, everything will be an advantage. And again, there is a privacy issue. If everything is running onto the car, onto the chip in the car, there is a huge privacy advantage because you're not connected to the cloud or anything. Okay. Just a general framework of how does a neural net works. I think we can skip this. Yeah, just a basic neural network. A nonlinear or generalized linear classifiers or a multi-layer perceptrons. I'm assuming everybody is familiar with these basic things in there, so I'm just rushing from them. Let's see. Yeah, and autoencoders and all. So one of an interesting problem to solve in autonomous is having a super resolution. How do you actually super resolve an image? And a regular image is okay, but let's say it's a LiDAR 3D point cloud image or a radar image. How do you actually super resolve it? So autoencoders kind of seems to be helpful in doing that. And again, if you wanna, as a research problem, having the super resolution for vision-based things is relatively easy because there is a lot of data and there is a pre-trained networks. But doing it for other sensors, I think that's very challenging, and it's a good improvement if somebody is interested. So okay.
A quick
so yeah.
question. So
Yes.
when we're talking about the super resolution, I think you mentioned that the major challenge comes from the other types of sensors, like.
Yes.
Okay. For example, if we're talking about radar input, is it still a 2D? Is it still a point cloud?
No, it's not actually. So radar, so the radar data, as to say, the radar outputs that are there is a complex number. It's an FFT
Oh,
values.
right.
It's an FFT value. So we're talking complex numbers here. And one way of doing it is, I mean, you can take a magnitude, just make it, a simple image, or you take phase and the what you call the magnitude separately. I mean, you can do that. But one of the other distinction, let's say from a camera and a radar, is that radar images are very sparse. So what you're looking into is like just an entirely empty image, and you see just one or two dots or points. And getting a super resolution on those points, and your job is to sharpen those points as much as possible. So doing them is the one that is challenging in there. It's a little different than doing it on a vision, where you want to sharpen or you want to have a high resolution onto the entire image. And then you have assistance from these pre-trained networks. That is easy. So one of the challenging tasks that I have is actually doing, let's say, super resolution on LiDAR or a super resolution on a radar. So that's tricky. And so yeah, you have to come up with all sorts of tricks there that you use. So yeah, that's there. Okay, so yeah, how do you stack these autoencoders and make it more deeper, more sort of dense and deep? So that's just one of the things that we have to do. Yeah, that's one of these insights that we have in when we're doing these deep learners training and all. Majority of the time, so this is one of the observations. Majority of the time, the kind of data that we have is not highly nonlinear, or is it not? It's not completely linear. It's somewhere in the middle. So the question that we always ask is like, okay, how deep we need to go actually? Because remember, the problem here is we do not want to just crazily put like 50 depth of deep learners or something. We can't do that. So we want to be very careful of how deep we want to do it. So the problem we ask is like, if you actually take out the features from each of those layers or the deep layers that you have, and you can try to see, is it linear enough or not? And there are ways to do that, like you have coefficient of determination and CODs, and there are a lot of parameters for that. If you can actually figure that part out, that how linear is these features, you will notice that the more deep you go, the more features get linear. But it's not always true. So you may not need, let's say, 20 depth. You might be okay with, I don't know, I'm just making a number, 4 or 5 depth. It should be enough. And then you also need to do some pruning there. So that's a pruning in let's say the horizontal direction of how deep you need. But you can also do a pruning in the vertical direction, in the number of hidden units that you take. So this is just one of the open problems that are there of how do you do the horizontal and vertical optimization. Yeah, this is one of my work before where I actually used a mean square error criteria for classification, and it kind of works pretty nicely. It's a very small network. The idea was just to put some kind of a nonlinearity, like a typical GLC, a generalized linear classifier outside on the outputs, and then use an approximate Newton's method to actually train this network. And it's easy to train it. And then it's easy to deploy it actually, because it's really, really small. The only challenge here is that in a typical MLP, the input has to go in this fashion rather than going it as an image. But this can be also plugged into the dense layer part of the convolution net that are there. Again, this is another of the work. This part was actually patented for an automated sorting machines in Dallas, and where there the job was to identify the different recycling items and then sort of sort them automatically. So again, they needed a really small network to actually work with, and this is where the idea of pruning kind of gets in. The hidden layer that are there, these layers, they kind of get pruned, and you really get a smaller network. And so yeah, that was one. We can skip this part, the growing input. Okay. I think people might be familiar with this already. Commonly used convolutional nets. I mean, yeah. So these are the interesting thing there is that if you just divide this whole image, that's what I find interesting here. Just take the image that you have. You have a feature engineering or feature learning here. The entire feature engineering can be by itself done independently, just taken out of the block. And then you have the classification done, which is the dense layer part that is there. So you can actually, when we actually deploy it into the car, and especially on an embedded, you have to do a lot of optimization part onto the embedded side that is there. So you, instead of taking floating points, you try to lower the precision there, or you do quantization awareness training, or you do mixed precision training. So those things kind of play a role. So it's kind of interesting here that how once you get the features or while you're training it, you can actually do those things. And then once you have the features, well, you can put any classifier you want to put. So that's there. Again, we also use recurrent nets because remember the entire problem is sequential. So I mean it's a car running on the road, so every frame is connected to the other one. So yes, that's a very common thing to know.
I have a question for the
Yes.
RNN network. This is interesting to know that RNN is also used in the overall pipeline. I didn't know that earlier. So is that for each stage of the RNN, it's a different stage of the autonomous driving, like planning, localization planning, perception, and control. So they are organized in RNN fashion?
Not all of them, for sure, because again, RNNs are heavy, they are computationally intensive, and I mean, I can go on with the problems with RNN, but mostly where it's being used is you kind of, again, like we were saying it before, we kind of go each problem has its own network that works, and then you have the global one. So this one, like RNN, is very actively used in perception. I mean, it kind of makes sense also because most of the perception task has sort of an RNN equivalent of it. Like have a convolutional and then you have an RNN equivalent, which is kind of doing the sequential job. But it's mostly for the perception tasks that we have RNN, or anything that has again a sequence to it. Let's say a tracking. A tracker has also there. That is there. But that's part of the job that we have to sort of find out those pockets of where the machine learning can replace something that is traditional. So I'll give you an example. I mean, Kalman filter is like the gold standard of tracking. So anything you come up with, you have to compare with the Kalman that is there. And if it works better, I mean, yeah, you got to convince a lot. So that's one area where you can replace a traditional tracker with a machine learning based tracker. But the main challenge there is the traditional tracker. Again, it has gone to the production. It has gone all the way there. It has gone to the product. It has a lot of steps involved. Like once you have a new algorithm and it goes to the production team, and then production actually makes it into a product. Because remember, these are like heavily tested things that goes onto the car. I mean, yeah, one accident is enough. I mean, take Uber for an example. I mean, like that Arizona accident just killed the entire program. Yeah. So yeah. So yeah, that's there. So yeah, I mean, but it's true for any of the critical systems. Any critical systems where machine learning is used, it's very true. Like even the medical field has the same thing. So the improvements are really slow, but they have to be really solid. So that's there. And the other thing I would add is there are no ISO standards for machine learning, unfortunately, so far. I mean, the government regulations are not that much. So what goes into the car and what's fair and what's not fair, there is no definition according to all the agencies and also so we face that problem also. The standardization is not there. So anyways, so yeah, these are most of the models that we actually use. I mean, these are every machine learning grad student might know this. So okay, yeah, most of the architectures that we have. Again, each of them have their own advantage and disadvantage, sort of. I mean, pyramid pooling, the last one, is something that we actively used in semantic segmentation. So yeah, that's there. And again, just to add to your point, Callie, is the urban setting has its own challenges and own problems, so we come up with own solutions for that. For example, semantic segmentation is extremely useful for urban setting as compared to a highway setting. It really advantages there. So yeah. Okay,
By
so
the way,
let's
sorry to interrupt. That actually brings me probably to another question. So if
yes.
you're using different strategies for highway driving and for urban driving, and maybe sometimes for school area driving, do you actually switch the model that you're using?
Oh yes,
Or
well we don't switch the model, but what we do really is that the car actually senses it. So what I was saying about there is a bigger structure that kind of takes care of everything. It kind of knows that okay, now we are in an urban setting. So and plus it gets information from the map. So the map is actually telling it like, oh, now we're in a school setting. So it kind of shifts towards that. So that sort of the conductor of the entire thing is kind of making sure that it's kind of working on all directions. But from the research perspective, we are very focused on the problems that we're solving. So let's say, I'll give an example. Let's say we are solving stationary objects detections. So what we do, once we have it set up, the model is there, trained, everything it's deployed onto the car. We literally put something in front of us on like let's say like a neighborhood road. Nobody's watching us there or something, somewhere that the police doesn't come. Okay. So yeah, we put in there and then we actually drive the car and see does the model that does the hypothesis that we actually, does it really work or not? And that's how we test it out. And then later on, we just take the car or just go on for a ride, go on to the highway, go on to the downtown or wherever, and then collect and then see how the network is behaving. Because it's really hard to get the edge cases done, frankly. The edge cases is very challenging because this whole approach is data driven. And the problem with that is sometimes we do not have data for. Let's say, I'll give you an example, which is an active area of research. How do you react in case of an accident? It's really hard. It's really hard because the amount of data. I mean, I'm not going to have accidents data set collected somewhere. Who's going to sit in that car? I mean, so it's a problem by itself. And that's coming because the entire machine learning is a data-driven approach. So yeah, that's an area of research by itself. So yeah, I think it's yes, please.
Dr. Tyagi, I just had another question as to how scalable are these solutions over here, like in the sense that say that I remember you mentioning that you can't really increase the hardware of sorts, like when you try to increase a sensor which was like 50 cents costlier, that kind of created an impact. So I'm just wondering in the sense that you have a very limited hardware which you really can't change, I guess. So how do you account for, say, newer things, or say if you want to have some newer machine learning model, or you want to scale up your solution? So how would you do that in this scenario?
Oh, that's a good question. There are multiple answers to this. The research answer to that is they are scalable like any other machine learning algorithm because we are testing it on sort of terabytes and like really good amount of data. They have been exhaustively tested. So the R&D answer is this. The sales answer or the corporate answer to this is what we really need is another hardware that is specifically designed for doing machine learning applications. And that's what they have to push. But in order to push it, again, you have to convince some customer. Again, it's a consumer market. You have to convince somebody that, hey, how about you buy this $10,000 piece of hardware, which took me like, what, $50 to make? But, how about you pay me the money for this? I mean, it's almost like getting funding. It's the same thing. So, it's really hard to convince it. But what's happening now is that most of the OEMs they've already realized it, that they cannot get it done on their traditional hardware because it's really, really small. So what we do, what usually, and that's why you see all these players that are coming in are kind of a little slow, but that's just the nature of their business. They are very, very careful when they do things. When most of the OEMs do, they are very careful what they're doing. I mean, again, I always draw parallel with the medical field. I mean, medical field is the same way. They go slow because it's related to life. It's a critical system. So, if your phone software doesn't work, all you can do is restart. That's fine. But Here, somebody, it's a life and death situation. So what's going to happen, or what is happening now, is that there is a specific tailor-made hardware, and actually every company is trying to get their own hardware made um, to go forward with it. And again, cutting the cost on that hardware and then selling it. I mean, I can give you the numbers, that how much it takes to cost it and how much it is sold, but I can tell you it's a huge margin
Right.
because R&D cost is also involved.
Just to
And
add up on,
yeah.
oh, I'm sorry.
And just to add one more point in there, it's really beneficial if you can actually get it. That's why I was saying about the mixed precision trainings, or quantization awareness training, or weight pruning training, all these trainings. If you can do something on a smaller hardware, I'll take an example, Raspberry Pi, or something on a smaller hardware, that is very beneficial because its initial cost is so low. I'm not saying you put a Raspberry Pi onto the car because it's not safe, but yeah. Yeah, that's the thing. Yeah, please go ahead with the question.
Yeah, I just wanted to, yeah, there was something similar on the embedded hardware front. So, like, in your developing these models, do you map it to a particular hardware in the sense that is the hardware extremely parallelized for these models to work independently? Because I remember you telling that you're not doing multimodal, but you're doing like one task has one specific deep learning algorithm. So, what I'm asking is that do you map it to a particular core on a hardware kind of a thing? Is it parallelized, or how is it like? Does it work independently?
Yeah, okay. So yeah, so what happens is all these so I'll take an example, maybe that'll help. Each of these hardwares that we take, let's say we take one hardware. I'll take one example which is in public domain, Jetson Nano. Now, I don't know what's inside the Jetson, but let's say the Jetson Nano has this, let's say, multiple cores, and there is one core which is specific for, let's say, matrix multiplication. So what you do is that you make sure that all the algorithms, machine learning, non-machine learning, wherever the matrix multiplication is there, they go onto that core. So you parallelize it in that way. And then rest of them goes to, let's say, I don't know, DSP core, or let's say an A72 core is also there. Which is like the input core, which takes in the Ethernet, all the input connections, the HDMI, USB, Ethernet, everything. So you kind of divide it or parallelize it in terms of which task goes to which core, because every core has its own advantage there.
Right. Yeah.
So not just the machine learning ones. Yeah.
Thank you.
I actually have a related follow-up question. So
Yes.
I remember in your previous slide, you're showing that there are multiple cameras, and they must be taking different images. So do we have one single model that's processing all those inputs in a one big model, or we have different models sitting in to process different images?
Oh, we have one single model that takes in all the images into one.
Oh, okay.
Just one single model that takes it in. And again, you do a sort of a low resolution version of it. You don't take the entire thing. And that's where the what I was talking about, this one. Yeah, this one. That's where the feature engineering by itself comes very, very crucial. Because you got to take each image, you just take the features in and just stitch it all together. Only the features.
Okay.
That's just a clever way of doing it. Rather than stitching the image and then taking the features, you just take features from each. So you compress it in the front.
Okay. So is that safe to say that you first aggregate all those images from different camera sources or different sensor sources, and you sort of fuse them together or process them together before? Oh, okay. Because I remember that 2 or 3 years ago, I was talking to another Chinese autonomous driving company, and they said they are using a separate model for each camera. I think that's going to be heavy. That's going to be expensive.
Oh, maybe I know which company is that. Okay.
Probably,
I'm just
yeah.
kidding,
Probably, you know. Yeah, so
okay.
apparently either they are doing something not smart, or things have advanced now.
No, it's so all of this is so it's okay. On a serious note, all of this is actually governed by the hardware that you're using.
Right.
I mean, my life will be super easy if they told me, oh, just use a GPU and then you're fine. Oh yeah, no problem. That it's just the hardware. It's just you kind of go backward actually. You know which hardware you're going to use. And I was just saying Raspberry or Jetson Nano. You cannot use this hardware onto the car. Just the very fact that they are not even. Their temperature requirements are not that much. You can't use them on certain temperatures that you have. So because ultimately you're going to put it onto the car, which can drive anywhere in any hot,
Oh,
extreme cold. So there are some specification from the National Highway U.S. Authority where you have to have that much of temperature requirement. So these boards don't work actually onto the car. They're just for demo purposes, or you can
okay.
just make a proof of concept.
Okay, cool.
Uh, Dr. Tyagi?
Yes, please.
So you said that you wait for all the images to be aggregated, but earlier in talk you had said that you are using CAN to aggregate the images. So that
No, I think yeah, the CAN is used just to aggregate, just to take in all the data from all the sensors, not just the camera. So we have camera, we have IMUs, we have the GPS, all the different sensors, like lidars and radars, everything.
yes, yeah. So my point is that CAN is slower compared to your the working frequency of your CPU. So you are inherently increasing the end latency, like from image extraction to your final classification, you are increasing the latency. But so doesn't that hurt you? Because
I see. Well, no, not really, because the depend on which CPU are we talking. So the CPU that we have, I mean, it depends, and also depends what speed are you driving the car. So it's not just one CAN bus that we have. We have multiple of them. I mean, not just the CAN. I mean, there are other data acquisition systems that we have that works into takes in all. So CAN just works for very specific sensor. In real life, I'm saying in real life the way it works, you don't put everything into the CAN because it's gonna just stuck, and I've seen
okay,
it happening.
so I can assume that the data acquisition latency is very, very less than the compute latency.
Yes,
Okay.
yes,
Yeah.
yes. And a good amount of money goes into data acquisition. Okay, sorry.
Okay. Thank you.
Yeah, there are actually. I mean, if you're interested, there is a company called B Plus. It's one of the fastest data acquisition that we've seen, and so yeah, that and they charge you a lot. They charge you a lot. So yeah, I mean, I don't know if you have time, and also I think yeah, I have to skip this part, I guess.
But I think you could briefly talk about it. I think we
Okay,
will be
sure.
interested.
Yeah, I'll quickly go through this. Okay. So yeah, this is about how to understand a typical driving scene, and in this case, I'll be talking about the urban scenario because that's where most of the research is right now. Um, Again, this is a typical situation where you have a single or a double stage detectors. Um, right now, I'm just showing a 2D object detections that we have. Uh, this is easy to do comparatively, but problem becomes in if we have LiDAR and other sensors, and here I'm showing, let's say the LiDAR base, we want to have the depth also because camera kind of lacks that part of the depth part. If you have, again, you want to use a cheap camera, it's all comes to the cost. So LiDAR kind of works out handy there, and then, but again, you don't want to have LiDAR when you're testing it, because again, nobody likes to have sort of a LiDAR on top of the car. So yeah, it's just a thing. So again, there are multiple solutions for it. I've just given one of the references I found very helpful. When you just use a LiDAR only for the training, but then when you're testing it, you don't really need it actually. And then another aspect that we use is the semantic segmentation. I find this really it's a very active area of research, and I've taken this figure from a paper, so it's not me. There are lots of different architectures for it, and then like lots of different implementations for it. And if anybody is like working on it from a research, I feel there is a lot of scope in there, and there are a lot of open problems in there. So yeah, that's pretty much about it. So
That's